Welcome everybody to our AI rounds. It gives me great pleasure today to introduce Dr. Amin Madani, who is an endocrine and acute care surgeon at UHN. He's assistant professor at the University of Toronto in the Department of Surgery and cross-appointed to the Computer Science and the Faculty of Applied Science and Engineering. His research focuses on the surgical expertise and the use of technology to enhance performance in the operating room. And he's led a number of new innovations in surgery and bringing artificial intelligence into the operating room. He leads an independently funded laboratory called SARA, Surgical Artificial Intelligence Research Academy, where he has a multidisciplinary team that he leads in developing this work. So Amin is going to speak on artificial intelligence for augmentation of surgical performance, promises, perils, and realistic expectations. So Amin, thank you for being here. You can take it away.
Thank you so much, Chef, and good evening, everyone. Thank you to the AI Hub for the invitation to showcase our work. Let's get started. These are my disclosures. I won't be talking about any of these today. And I guess I have one more disclosure. I may or may not have used the generative AI for some graphics and some of the slides in this presentation. I'm sure you'll tell which is which. Just a little bit of background about my work. We're pretty lucky here at UHN and where we are in the AI Hub. We're really at this intersection of just an amazing place where so much collaborative work happens from the university, the Department of Computer Science, the engineers, and UHN with the clinical volume and the research infrastructure we have, being right across from places like the Vector Institute, where world-class people in AI collaborate together. So it's really a nice place, and that's allowed me to build sort of this work in surgical AI. The kind of work that I do really focuses on that intersection of how to make surgeons better, essentially. How do we improve our performance, bringing patient safety, innovation, technology, and education together. So that's kind of what I'm going to focus on. This is my lab. And some of the partners that I work with, we truly are multidisciplinary. And so if you're interested in this kind of stuff, don't hesitate to reach out. I'll try to keep this very super, practical and not too overly technical. I'll start out by giving sort of an overview of what AI, machine learning, deep learning, computer vision, some of these basic things. But then we'll really spend the lion's share talking about some applications for surgery and some challenges as well. I think we all know by now what AI is. I don't think we need an in-depth overview of that, but just suffice it to say it's everywhere today. When I started off giving these grand rounds, it was kind of like, AI is coming and this is what it could potentially do, but now it's permeated into every facet of society. The study of computer science that gives machines the ability to act, to think on a high rational level. And this used to be kind of the stuff of science fiction, but it's impossible to do anything now without having some kind of interaction with artificial intelligence. We've all seen the explosion of large language models and its revolution on everything we do today. Everything from writing grants, helping with manuscripts, helping with AI scribes in healthcare, to just about everything you can possibly think of. You can even write songs in the style of Taylor Swift about surgical AI. You can quite literally do anything. Deep fakes, generative AI, you can generate any sort of video, images of practically anything, promptable images. And those of you on social media, I mean, it's almost impossible now in many situations to tell what's real and what's not real. So the technology has come quite far. And this has spilled into healthcare, obviously. Over the last decade, there's been more and more prototypes and validation and clinical trials and many products that have gone through regulatory clearance, Health Canada, FDA, and so on, and have actually been used in a clinical setting, whether it's in for radiology, for risk predictions, and things like that. There's now an explosion of AI scribes that are available, algorithms that listen in on the conversation, summarize a clinical encounter for you, algorithms that'll summarize a chart for you so that you can spend more time with the patient. And there's actually now studies that demonstrate that it helps improve things like physician wellness and being able to focus more on patient interactions as opposed to administrative burden. So this stuff is here to stay, and it's changing everything about healthcare. So that's AI. I mean, so what's machine learning? Machine learning is really, it's not the same thing as AI, but it's really the subset of AI that has made, given AI its abilities as we know it. It's basically the study of, we think of a traditional software, you code a program of software for every scenario. In machine learning, it's very different. It's basically training an algorithm to detect patterns and being able to make predictions on new data that it has never seen before. And so there's different ways to train a computer code to do that. And deep learning is the subset of that, of machine learning, that has really given many of its abilities to do that. The first example is supervised learning. That's probably one of the most common ones you'll see in the literature, but essentially it's saying, okay, AI, I'm going to teach you how to make this kind of prediction for this tasks. Here's a bunch of examples. In this area, in this, if you see this is an apple. You see this is a banana, this is an orange, this is a grape. And you do so many examples of that until it becomes really good at making that prediction. And it sees an apple that it has never seen before and say, okay, I've seen that pattern of that shape, that texture, that shininess, and so on. That's 98% probability it's an apple. Unsupervised learning is a little bit different. It's basically, there's no labeling of data. There's no saying this is an apple. It's basically, here's all the data, find patterns amongst this data and clusters, essentially. This is very common in things like e-commerce. So when you find things like your Netflix, it's able to give you personalized predictions on what you're most likely to watch next and become hooked on the next show. It's because it's categorized you into a specific pattern, whether it's your demographics or your previous watch history or where you live, and so on and so forth. So this is unsupervised learning. And then the last one, which is, I think, really interesting, is called reinforcement learning. It's essentially saying, okay, AI, I'm going to teach you how to do this thing. And then you put the AI in a environment, a simulation, or it could be a real world. And then you give it a function that it has to optimize, or we call it a reward function. And basically, the AI agent will undertake actions in that environment. And it basically gets a reward or feedback on whether or not that led it more and more towards optimization of that thing it needs to optimize. So it's kind of like positive reinforcement, negative reinforcement, most similar to how we humans learn, essentially. And it keeps doing that until it finds behaviors that make it become better and better at that task. This is an example of one of the first algorithms to use reinforcement learning is for Atari Breakout, before my time. But essentially, after 10 minutes of training, it's not really good. But then after 2 hours of training, it becomes really good. It understands that which patterns of movements will optimize its score. And then after 4 hours, not only does it become really good at that, but it becomes very creative at finding solutions, like concentrating the ball in the corner. Deep neural networks are a class of algorithms that basically are designed after the nervous system, where you have an input of data that comes in from that's your input layer of the neuron. Then you've got hidden layers, and that's where a lot of the pattern recognition happens. And then you have an output layer. So if, let's say, the task is to identify what's in an image, the input layer is basically all the pixels in that image. And then basically, through a lot of training, the algorithm is able to tell, okay, well, with this shape of a beak, the texture of this feather, it's able to kind of associate those high-level features of the image and say, okay, that's associated with the bird output. So that's kind of how deep learning works in a high level. There's a lot of applications. An area that's a focus for me is computer vision, AI to be able to achieve perceptual functions. like saying what's in a scene, object identification, recognition, and tracking. So it can say like, okay, in this image, there's a koala on a high level. That's a classification task. And it can also localize it with a bounding box. You can even outline an object. In this is called segmentation. It can also track, and this is like an example like of boxing. An algorithm can tell exactly where the punches have occurred, where it occurs, and so on. At the end of the day, machine learning is pattern recognition. That's all it is. We think of AI as like intelligence, but it doesn't. There's no intelligence. It doesn't understand larger contexts, and it's very subject to how it's trained. Some of the first algorithms that came out demonstrate this very nicely. This is a text-to-image prompt of salmon in a river, and it literally has a salmon in a river. It doesn't understand the context of what you're trying to do. It's kind of a disgusting picture. This one is eggplant, so it doesn't understand, some of those principles. The models are now better, but this is just kind of demonstrate this concept that it doesn't understand the larger context. Okay, on that, let's pivot and talk a little bit about some of the applications for surgery. There's sort of 6 categories that I'd like to think of surgical data science, and sort of they fall into these categories, and I'll try to highlight as many as I can. Why is this important, especially the stuff on intraoperative decision support and AI to make surgeons better? Why is that really important? I think it's always important to kind of take a step back and understand, why do we need this technology? And the fact is, hospitals are very dangerous. There's always a high rates of adverse events, especially surgical patients. Surgical complications are actually extremely common. Doesn't matter what subspecialty you're in, what part of the world you're in, they occur. And the majority are actually preventable and can be traced back to something that happened during surgery, often technique related, something related to decision making, judgment, situational awareness. So the burden is quite high. And if you actually do a deep dive, what caused those complications or adverse events around it? A big chunk of them are actually related to a lapse in judgment or lack of situational awareness, that then lead to suboptimal performance and negative outcomes. So this is an example of me doing a thyroidectomy. I'm dissecting on the recurrent laryngeal nerve. This is the nerve here. So what does it mean exercising good judgment, good decision making? It's knowing exactly where to grab the thyroid here and lift it up in this vector. It's knowing the path of this nerve is going to go up and then go back down, and there's an avascular space. It's knowing that you have to rotate the thyroid on the other side in this perfect vector to provide countertraction. All of this collective of decisions is what drives surgical expertise and good outcomes. And you can actually map that out. This is for adrenalectomy. All the things that your surgeon has to think about to go from point A to point B of the operation in a safe and effective way. Every one of these items is something that's very crucial or important. The key is to identify where errors occur in this map and design algorithms to intervene. So can we use surgical AI to do that, to use see what's happening in the surgical field, and give us some real-time guidance, decision support, kind of like your co-pilot, and be able to give you augmentation of your performance. You guys have, I think most people have heard sort of our first prototype. This is called the go, no-go zone for safe laparoscopic cholecystectomy, gallbladder removal. And basically, every surgery has this concept of go and no-go zones. A lot of the structures, the anatomy doesn't come beautifully dissected for you during a surgery. Oftentimes it's hidden under fatty fibrous tissues. It's unclear where to go. It's unclear where it's safe, where it's not safe. And you have to kind of figure your way out during surgery. But generally, surgeons have this general idea of where it's safe to kind of go in and where it's not safe to dissect in. So we call these go and no-go zones. So we said, can we train an algorithm to define these for gallbladders? Conceptually safe, a simple principle, but it takes a lot of practice and training to derive that pattern recognition. So that's hard to do because namely, surgeons don't agree on anything ever. If you put 2 surgeons in a room, can you imagine 10 surgeons agreeing on anything? Now imagine asking them, okay, where's the best place to dissect? And then asking them to annotate. They're never going to agree on every single pixel. So we had to figure out some creative ways of finding what expert consensus is, and then train our algorithm algorithm that way. So we trained a deep neural network. We used supervised machine learning. We gave it a large data set of hundreds of videos from around the world, different geographic locations, different surgeons, different patients, different healthcare systems even. We asked them to annotate. We trained our neural network, and now we had a model that can predict go and no-go zones. And this is what the model looked like, the first prototype. Every single frame, it's analyzing where it's safe, that's the green, and where it's unsafe to dissect. So now we finally have like an algorithm where it projects my mental model of how I see the surgical field. And this algorithm has undergone different iterations. There's different ways to skin the cat. Like, there's different architectures of AI that you can do. Some are better, some are faster, some are more computationally expensive. So if you want to use something in the operating room, you have to make sure that it's not going to require an insane amount of hardware to run that algorithm, and it has to be practical. So there's a lot of different ways to do this. Ultimately, regardless of what you use, this is a video of a bile duct injury. The hot spot here is where the go zone is, the safe area, and you can see the dissection is happening well below that safe area. This is just millimeters, but those millimeters are enough to cause a bile duct injury. And unfortunately, this structure below the go zone is being clipped and divided. So the idea is that can we use this to avoid that? Since then, we've developed a lot of algorithms, and the literature is now full of these kinds of algorithms. Doesn't matter which body part you work with, whether it's in the lung, in the breast surgery, colorectal, bariatric, even brain surgery, there's an algorithm for you. This is an example for colorectal. I'll just kind of highlight a few. An algorithm that tells you where the oncologic plane is for colon cancer. And this is where you want to dissect to avoid either taking too much tissue or too little tissue. And these are some of the videos from our partners in Japan who have developed some of the early algorithms for colorectal surgery. This is for gastric cancer surgery. One of my postdocs from Korea developed an algorithm to predict where is the safe area to dissect for gastric cancers. So this is the pancreas here, and these are the lymph nodes that need to be removed. So it delineates the go zone for dissecting your cancer. This is the work done with in collaboration with Tom Forbes in vascular surgery. They want an algorithm that can say, okay, do not deploy your stent for an aneurysm above this level where the kidney, the renal arteries are. And so they wanted a no-go zone projected on fluoroscopy during a endovascular AAA repair. And so this was published 2 years ago. For quality improvement, it's very important. So this is called the critical view of safety. For gallbladder surgery, you have to achieve what's called a critical view of safety. This sort of checklist before you divide the cystic duct and cystic artery. It's sort of like a checkpoint below it, and if you don't achieve that, you shouldn't divide anything because you can get into a major bile duct injury. This is a work out of one of my undergraduate students, Raphael, who developed this beautiful pipeline of a digital ruler. Oftentimes in surgeries like in intestinal surgery, you need to measure the length of the intestines, or you need to measure a hernia defect. And so oftentimes we kind of have to estimate, or we bring a ruler inside the abdomen, but now we have an algorithm that'll basically do that for you. AI has been really useful for an area called digital twins. Digital twins is our dynamic virtual replicas, basically, of a physical system, like a patient, an organ, or a surgical environment, and it continuously updates using real-world data or something that you can interact with very dynamically. And it's being touted as sort of an area that allows a lot of personalized simulation, preoperative planning, rehearsing an operation before the fact to see what would happen if you do certain things. And a great example of this is actually recently published by Schaaf's group and Andrew Sage, who developed a digital twin for lung physiology on transplanted lungs to be able to predict what the physiology and the biochemistry will look like. So you can simulate interventions on those lungs and see how they'll behave. That's an example of a digital twin. This was just published in Nature Biomed Engineering recently. So we started using digital twins for preoperative planning simulation. basically taking images like MRI, CTs, and creating these 3D renderings of the models to use it for patient discussions, preoperative planning, simulating a surgery, and so on. Now, this has been around for a long time, but 3D rendering is not new. There's at least 2 decades people have been doing this. The problem is just not a scalable solution, and it's very, very labor intensive. So we've been using AI to automate the ability to circle your anatomy on a CT or MRI to do your reconstruction. The other problem is there's a lot of nuance to it, and letting the AI to automate your 3D reconstruction is actually not a smart way to do it, because you want the human in there to say, okay, this is my tumor, and this is the very nuanced anatomy that I want in my 3D model, especially for things like breast cancer, where it can be very multifocal tumors. You need a human, a breast surgeon, to say, these are my tumors, and I want that in my model. So you need that human in the loop, and that hasn't been done yet. And also there's integration into your system. Right now, it's very difficult to have this streamlined at the point of care. So for the last few years, we've been doing that here at UHN. We've created a pipeline that's now integrated into our packs. So your surgeon can actually choose your AI model, put in the accession number of the MRI or CT or whatever, and the span of 30 seconds get a 3D reconstruction. And you can actually bring this in your OR and use your hands to kind of move around the model, so you don't have to scrub out. These are our partners at Mount Sinai who've been using it for orthopedic oncology. And remember, I said it allows you for a nuanced way of identifying tumors. So in this case, they're selecting the tumor using the CT scan. They're saying, this is my tumor. And then within a few seconds, they get a reconstruction that shows their tumor and the humerus and all that. This is a case that I did several weeks ago, an adrenal. Basically, I brought up the CT scan. I said, okay, this is my tumor. And then within seconds, I was able to do planning of my tumor and exactly where I want to put my ports, because I use a retroperitoneoscopic approach. So all this is something that we've now been able to streamline. Our breast surgeons are very excited about this because they can use this for preoperative planning, being able to simulate where the tumor is. You can actually do some detailed analysis of where to create your flaps during a dissection. You can actually use it to mark out the distance of the tumor to the skin, so they can do localization. And you can also simulate, we're now getting to the point where you can put physical AI in it and be able to simulate what the cosmetic outcome of an incision will look like, so they can have discussions with their patients. I think the future will really do a lot for us. I think we can then take these 3D models and actually do deep fakes. You can actually simulate surgery. This is a deep fake of a surgery by a group out of Germany that basically took 3D renderings and simulated what the intraoperative anatomy would look like. So there's a lot happening in that field. Switching gears a little bit on surgical education, AI can be used for a lot of things, for teaching, for coaching, performance assessment. Traditionally, what this does is it uses a lot of kinematics data, tracking of instruments and hands, to be able to say, okay, this pattern of movement is very similar to what a novice would do and what an expert would do. You can actually do this with your, like this is me on a webcam. You can track every joint in your body. These algorithms are widely available now. And there's a lot of studies published. This is on an example several years ago, actually, that tracks your hand motions and is able to look at suturing tasks and knot tying tasks. And it's able to, they trained an AI model to be able to predict the performance of those trainees. And they compared it to what experts would have rated them as well. And you can see there's a really strong correlation. But what's really great here, and why I highlight this, is there's a lot less variability. It's a lot more consistent to use the AI models for these kinds of things. So I think surgical education will change a lot. You can also use it for credentialing. This is work done out of Japan, where at a national level, surgeons are required to submit a video of themselves operating for colon cancer, and they get rated by experts. And basically, that decides whether or not they're allowed to operate on patients. So these guys developed an AI algorithm to basically, it has a similarity index that predicts how close it is to the perfect surgeon who does this, and they're able to show very high correlation compared to what experts would rate that as well. So it looks very promising for credentialing purpose. But what about coaching? Like actually providing a surgeon with very nuanced, very personalized data on their performance. Surgical coaching is a thing that's very important, but it's very difficult to scale this. Having a coach that's always available, time, geographic constraints, and things like that. It's very challenging to do that. So this is the work, a lot of work being done in this field, and I'll highlight some of the work done by one of my master's students, Ziad. Basically, as I said, algorithms can track tools. That's great, but no surgeon will really care if you tell them your pattern of movement is like this. That's not very meaningful data. We also have algorithms that'll tell you where things like go zone and no-go zone are. But again, it doesn't tell you what you did in that surgery. So we need algorithms that can give you details on your intraoperative behaviors, actions, and techniques. Some of the preliminary work we've done here is around retraction. This is an algorithm by one of my older postdocs, a Japanese surgeon, Dr. Yoshida, that assesses your degree of retraction during lap chole. We've replicated this for colorectal cancer as well, and it's able to predict retraction for that as well. It's still not perfect. It's still a work in progress, but we're slowly getting there. This is the work done out of our friends at Mount Sinai. They were able to basically analyze videos of prostatectomies, and they were looking at every single dissection technique that happened. They call it surgical gestures. There's different ways to dissect, with a hook, with a peanut, using the cautery, and so on. And they were able to map out all the different patterns of gestures that happen and which are associated with better postoperative outcomes. So we're starting to get better at doing that. This is the work of, like I said, my master's student, Ziad, who basically developed an algorithm to provide people with very specific details on their behaviors, giving a very objective feedback, automated feedback on exactly what they did. We call these tool tissue interactions, an algorithm that can detect exactly what you did, how you did it, and where you did it. So we basically correlated these tool tissue interactions with go and no-go zones. So we can say, okay, can you tell how a surgeon dissected, whether or not they were safe or unsafe? And then we validated this on a cohort of safe and unsafe videos. Unsafe videos being those that had injuries. So when you compare the safe laparoscopic cholecystectomies to those that had bile duct injuries, you can see a big difference in dissection technique. Clearly, the ones that had an injury, there's a lot more dissection in no-go zone that happened. So it's very clear that you can pick up on those nuances. This is an example of one. The algorithm is detecting interactions happening in the no-go zone, and it highlights that. And you can actually look at it throughout the course of an operation. There's like a cumulative addition of no-go zone dissections that happen. And it's not that it detects injuries that happen after the fact. It actually, within a few minutes, it's actually able to tell you're diverging away from safe surgery. This is very clearly a pattern of unsafe surgery, and it can kind of highlight that within minutes. And the algorithm is able to detect most injuries that are bound to happen. It doesn't detect all bile duct injuries, but it is able to detect the lion's share. And so algorithms like this can be used to give people postoperative video feedback, like a scorecard, some very personalized feedback, and also being used during surgery to tell them, hey, you're diverting from safe surgery. You can also use digital twins for coaching purposes. This is the work of another master's students who's developed 3D models from surgical videos, and you're able to basically take videos that you've done and actually manipulate the tissues here, in this case a gallbladder, and be able to predict things like the biomechanical properties of the gallbladder. So in this case, we're using it to teach retraction, how to best grab the gallbladder to retract and expose for you. Switching gears, perioperative care is an area in surgical data science. I'm not going to go into this because it's not my area of expertise by any means, but there's a lot of algorithms that have come out to predict deteriorating patients or predict who's going to have a good outcome or who's not going to have a good outcome. Also in the operating room too, there's algorithms that can look at the waveform on the anesthesia machine and predict who's going to have like a hypotensive episodes, for instance. So there's a lot happening there. I think a really hot area also is patient flow and resource management. There's now a lot of work being done on algorithms that can figure out what's happening in the surgical environment. What's happening in the OR? Are they draping? Are they done the case? What part of the surgery are they at? What's actually happening at the action level of a surgery? So that, let's say your charge nurse knows well ahead of time that you're about to close, so they can start getting the next patient ready. And there's a lot of vendors that now sell these kinds of products as part of their offerings to say that they can make you more efficient. Now, whether or not it's valid or not is another story, but that's sort of the claim. Our group has taken that to sort of another level. This is the work of Lawrence, one of my prior master students who has now moved on and works as a machine learning specialist in the lab. We said, okay, can we use an AI to optimize workflow and patient transfers and triaging and dispatching on a city level, like on a large scale level? And so we use mass casualty trauma incidents as the use case, where you're supposed to be able to triage and dispatch patients to decide where to send them to. Obviously, the most injured patients go to trauma centers. The ones that are not as critical go elsewhere. It depends on hospital factors, ICU beds, what transportation is available, how far they are from the hospitals, and so on. So, and you can see it becomes a big problem when you have even 20 patients. There's 180 possibilities. So what we did was we used reinforcement learning. We created a simulation, in this case, the city of Toronto, and we trained the algorithms to be able to practice decision making again and again until it becomes really good at it. This is the first iteration of the model. It's like a user interface. It's like a video game, if you will, where the commander has to decide where to transfer people to, and the AI gives you sort of a recommendation of where to transfer someone. And this is good for simulation. As you know, they're doing simulations for FIFA, for instance, in the summer. So getting the entire group together to practice how to triage, dispatch, and manage people is quite challenging. So systems like this can be helpful for that. This is the latest iterations. You can look at the lay of the land. You can see where all the ICU beds, ventilators, and so on for something like a COVID public health disaster. The latest algorithm is also more advanced. It actually gives you explainability as to why you should send somebody to, say, Sunnybrook as opposed to, say, Mike's, and then gives you alternative examples and so on. So it's becoming more advanced, more detailed, more interactive. The military is very excited for this because you can actually use it for battlefield triaging and distribution, medevac coordination, and also practicing, rehearsing and readiness training. It is also very important for repatriation. So God forbid there's like a war somewhere that suddenly we have a lot of casualties coming back to Canada. Where do you load balance them across Canada? Where to transfer them, which hubs in which airports to send people back to. This is a very big problem. And so we've designed AI algorithms to help with these kinds of situations as well. When you look at the data, we looked at humans and human with AI. We looked at non-experts and experts. And clearly when AI is being used, performance is better for both groups. Funny thing is, when the AI is used, the delta between expert and non-expert is pretty much gone. So it helps bridge that gap. So these kinds of things will be used in a lot of things like military and civilian applications. A word on autonomous surgery, because this comes up all the time. People ask, is AI going to replace surgeons? Instead of augmentation, is there going to be a bunch of Terminators walking around? I don't think so, but the reason why this is actually important, it's not necessarily Terminators walking around, but adding intelligence to robotic surgery platforms. Instead of having arms that you control, it's controlled by AI algorithms. This can help with dissemination of skill one day, especially if robotic platforms become a lot cheaper, and standardizing surgical care. It's kind of, think about current robots today as master-slave relationship, kind of like a marionette that you're kind of moving around. The is to give future robots the autonomous ability to see, think, act, and so on. To my knowledge, the only platform I know that has implemented any automation is Moon Surgical, which basically does very, very simple things like camera navigation. And then you'll see a lot of things like, studies that have been done that'll claim that there's one study that came out very famously a few months ago that claims that it can do gallbladder surgeries as good as experts. And this is completely wrong. There is so much nuance to that, and I can assure those surgeons on this call that AI is not going to replace surgeons anytime soon. Not with this. It's still very, very far away. But claims like it's as good as experts is just completely faulty. There's still a very, very, very long way to go, and we haven't even scratched the surface of the complexity needed to automate an entire surgery. Let's talk about challenges to end this presentation. A lot of the things I talked about was on this sort of first part of it, the data science, but then actual implementation for value generation is really the biggest challenge I find, is the operationalizing piece. There's so much that goes into that. Like our first AI algorithms came out years ago, and we are just starting to implement them in the operating room. And the operating room is a particularly complex environment where it's very time sensitive. There's not a lot of room for error and technical glitches. It's not like in the clinic using an algorithm for predicting someone's outcome after surgery. That's not high stakes like surgery. So there's a lot more nuance to surgery than other AI applications. Infrastructure, deployment strategies for real-time support. How do you scale this to low resource settings where you're limited in compute power and bandwidth and Wi-Fi? How do you generalize your model to local institutions is still a big problem. You want to optimize your model for use for real time. And then there's a lot of design considerations too. A lot of our work in the lab over the last 2 years, has been focused on building that infrastructure, this whole end-to-end pipeline of everything from data coming in to using that data into a machine learning pipeline, creating a library of AI algorithms, and then having those AI algorithms available for dissemination in the real world, whether it's on cloud, whether it's live during a surgery, and so on. This is an example of some of the work we have done. We've created this sort of plug and play system where the surgeon has an app on their phone. It pairs with the system in the OR, and they literally go like an app store, select the model that they want for their surgery. They select their preferences, the colors, and all that, and then they deploy it. And you can see this is the fourth floor of Toronto Western Hospital. If those of you who've been to the fourth floor of Toronto Western Hospital ORs, you'll know it's a very old operating room. There's nothing fancy about infrastructure there. You can see the rolling cart of laparoscopy, and we're able to use it in that setting. You can pretty much use it anywhere. You don't need a box or any hardware. You can actually take that data on your phone, on your video, the video camera on your phone, and be able to stream that on the cloud and get real-time AI inference on your phone as well. So we've kind of implemented those solutions too. This is the work done by one of my other master students. We looked into different deployment infrastructures, like on cloud, using edge computing and things like that. The cost, the benefits and downsides of one versus another. And suffice it to say, there's a lot of pros and cons of one or the other. There's no one size fit all here. If you're on cloud, it's cheaper, but then you face a lot of security compliance issues. You're going to face a lot of lag, especially if it's real-time, frame-by-frame guidance. If you want something for really high performance, then you need to bring the compute in the OR. That obviously has more cost and things like that. So there's a nice paper coming out on that topic soon. You have to remember that there's a lot of latency problems as well, especially for go and no-go zones. I don't know if it shows on people's monitors with the Wi-Fi, but the one on the left is very choppy. The one on the right is more smooth. Do you need AI to inference every single frame? Not necessarily, especially if it's just a snapshot. I need an assessment. Have I achieved a critical view of safety? Yes or no? And that's it. But if it's frame by frame, I want to look at this and do my surgery, then you need more frame by frame analysis. So there's a lot of design considerations there.
generalizability is a problem, like I talked about, and especially in medical imaging, there's a lot of like algorithms that are developed to detect, like, say, breast cancer or things like this. But AI is notorious that if you don't use data set from your institution, you go across the street to another hospital, it's notorious for performing not as much as it has in your institution. And that's because of things and different technical details of the data that it's used, different resolutions, different frames per second, the different aspect ratios, all of that plays a role. You can either start off with a large data set that has high level of heterogeneity, like we did with go and no-go zones, or you can use more creative ways, like we did here with breast cancer. So we trained an algorithm here using a data set from Duke University. We said, okay, we trained a model on Duke data, and then what we did was we used that model to do the annotation on our own UHN data with a human sort of correcting where it was wrong. So AI did sort of a lot of the labor-intensive work of annotation, and then we trained. Then we had a labeled data set from UHN, and we trained a new model. Now a new model that works on our data. So you can get a bit creative around that as well. And obviously, design considerations are very important. You need to test usability, human factors. In this case, for no-go, no zone, people wanted to know how confident is the model. So we had to integrate some heat map. The transparency in this case is a reflection of the confidence level of the model. And you can actually decide. So only make my model predict if it's above 80%. So these are all design considerations. And you want to evaluate your model, there's a lot of things you can do. There's a technical performance, qualitative assessment, human factors testing, and then obviously clinical trials. First, you would do a silent trial ideally, and then you would actually do a real clinical trial. Ultimately, though, it's very important, and we don't say this enough, but for this kind of AI research, it's always important to take a step back and understand what is the problem that we're trying to solve. In this case, we're trying to make surgeons better. Well, we need to first understand where the problems are and design a solution very, very specific to that unmet need. And I find we don't do that enough in this area of research. So it's important to map that out and look at the where errors happen, where that lapse in judgment happens. But ideally, this kind of solution is very exciting because then you can package the collective wisdom of expert surgeons into software that you can then disseminate around the world. And the example I always give is of my friend Kaya Schwartz. Just recently, we did a surgery on a very, very difficult surgery that I could not have done without her expertise. And what this allows to me, what the value of AI here is being able to capture her expertise, but not just hers, but all the other Kaya Schwartzes around the world, and create like a superhuman that has that expertise of all those experts into one that you disseminate. So the world of surgery and digital surgery is very excited in the coming years. I'll end it here, and I'll just summarize that AI is a very powerful tool. There's a lot of use cases in data science. Computer vision for real-time guidance is really in its infancy, but we've come a long way over the last few years, and operationalizing this for intraoperative use has many obstacles, but ultimately this technology can improve quality, safety, stewardship, resource optimization, and provide more equitable care and do things like democratize surgical care. I couldn't done this without the amount of help from my lab members, all the students, the postdocs, my lab manager Kathy, just putting this presentation together and looking at all the work that we've done through digital twins, AI models, infrastructures, workflow and everything. It's just, it's pretty exciting. And a big thank you to all those students who have put in all the work to make this happen. Thank you.
That's a great talk. I mean, very, very exciting for all of us as surgeons. Well, Kelly will unmute you, so if you just put your hand up, I can field questions. I think I can see everybody. I'm not sure. Oh, good. Sarah, you got a question?
Hi, Amin. It's Sarah Mudd at CIO. You and I have had a quick chat, and I knew you were up to stuff. I had no idea you were up to this much stuff. So it's very, very impressive. And
Thank
I've
you.
got two questions for you. One of them is, how did you wake up one morning and get yourself into this? I mean, you probably have a traditional surgical training background. I'd like to kind of understand how we generate that interest and replicate the kind of leadership that you're providing. And my other question is about the uptake in surgery. And do you find that the surgeons are open to some of the new interventions? Are they worried? What does that change management look like? And again, very exciting work. So a little bit about yourself and then a little bit about your peers.
Thank you, Sarah. Really appreciate that question. I think I don't think I ever woke up one day and said, "Oh my God, AI." I think my background just kind of naturally flowed into it. I did my PhD in surgical education, so it was really about understanding, and I was so fascinated by the deep dive of understanding, surgeons like Schaff. Like, why is he so good at what he does in the operating room? And I was a trainee at the time, and I was like, how can I think like these experts? So I was just so fascinated by how they visualize a surgical field and how I see it. And a lot of my work was around doing that deep dive to understand the mental model of expert surgeons. And we actually, unbeknownst to us, I was developing a software at the time for annotation, where we had these frames of videos. We said, okay, here's a gallbladder. Where do you want to dissect? And then we would compare that to what experts would do. And so the students and trainees would get feedback on their decision-making skills. But unbeknownst to me, that was actually an annotation software that we developed. And so when then I met a partner who was doing a lot of work on AI and computer vision and so on, and he kind of introduced me to the world of AI, and he looked at this computer annotation software we developed for teaching purpose, and he said, "This is exactly how we need to train AI." And I was like, I'm like, "What's AI?" And that was only in like 2019. So we've come a very long way. I think that in terms of what we can do to help the next generation of students and people who are interested in this is, we have so many resources here available to us. There's a lot of projects, and I think it's about fostering an environment to, to nurture that kind of curiosity and interest. I think, every time there's somebody who emails me, asks me about potential projects, I do my best to give them something to, something very tangible that they can work on, and along the way, learn about AI, machine learning, computer vision, and things like that. So I think it's, hopefully we can, formalize it in some way into medical school training. Perhaps we can provide, I know there's a lot of work being done in AI literacy at UHN, and I think those are all paths to improve and increase engagement in this very exciting area. Whether or not surgeons are excited, I think people are excited, cautiously optimistic, and I think that's the right attitude to have. Obviously, there's a mix. Some people are more optimistic than others. Some are like the very early adopters. Some are like, I don't want to be involved. And I think it's about just kind of making sure people understand and being honest about it. And I always tell, like, I'm probably going to be the most critical about my own AI algorithms that I develop, because you just have to be very honest about what it can and cannot do. And in the moment we start overselling this is the moment we lose trust in potential adopters. And so when I kind of use that kind of approach, I find that our surgical partners are more willing to participate and give their feedback. And ultimately, of having people engage is how we make this technology more usable for the next generation. Yeah.
I think the other part, Sarah, is that a lot of surgeons like new toys, and this is part of it. But the other part of it is surgery can be humbling. Human anatomy has variations. Tumors do weird things, and so if there's an opportunity to make it easier or make us better or make us less likely to have an error, I think that will appeal to surgeons, that this takes some of the guesswork out of it, and it may actually shorten training. because a lot of what we've done, it's putting in the years and years of repetition and recognizing when there's a trap and you could get into trouble here and so on. Like, what if you had something that could warn you that there's a trap, and that sort of thing. So I think that's really good. The other thing that Amin and I have talked about a lot is we have the most amazing and sophisticated medical imaging available, and it continues to improve. And yet we don't use it as much in surgery. We haven't been able to get it in the operating room. So can we get, overlaid images? Can we get GPS type navigation in the body? And I think that's a huge opportunity for us that will make surgery safer, but also allow us to do things that we couldn't do before.
Terrific. Thank you. Thank you so much.
Thank you.
Question there? Who's CM?
Hi there. Can you hear me?
Yep.
Yeah.
Hi. Pleasure to meet you. My name is Caesar. It's wonderful what you're doing. Just as a brief summary, I'm an MD. I have a master's in data science, and I just recently finished a program in cloud engineering. So basically, I understand the scope that you're doing and scope and the development of models and scope of the deployment. And it's just amazing.
Thank you.
Oh, by the way, I'm visiting you from Mexico.
Okay.
Okay, quick question. How do you manage, the retraining in model drift? And if so, like, when or how are you capturing new data to retrain the model, and how do you monitor that?
Oh, I see. You're talking more about like long-term, constantly making the model updated and better as new data comes in.
Yes, exactly.
Right. Oh yeah, no, that's a great question. And about model drift, we haven't, the truth is we haven't gotten there. I think everything we've been using is all on retrospectively obtained data. The end-to-end pipeline does not allow currently for you have an algorithm, it takes new data in the operating room, gives you guidance or whatever it is, but then it also annotates that new data and then feeds it and retrains it. I think that's a whole different layer of complexity. And also, not to mention, I don't think the algorithms are good enough right now to train themselves, at least not in these applications. So we haven't gone down that route. But I know a lot of models, like risk prediction models, do. But we don't do that with computer vision, just because there's just so much human supervision that's necessary right now for those annotations. So that cycle of constantly making itself better is just we're not there yet.
Yeah, totally. And I'm actually the first advocate to not integrate AI in this kind of workflows. And this is the first time that I agree. And the way that you've built it, because there are a lot of buzzwords and so forth that also on the clinical side don't know, but now that I'm in the development and training side, I know. So there's a mismatch, and what you're doing is wonderful. Just one final question. Is it possible I could contact you?
Yeah,
for help
absolutely.
if possible?
I'll put my email in the chat, so that way everybody has it, and don't hesitate to reach out, guys.
The other thing, I mean, is the thing people have alluded to. Will robots be doing surgery for us? And last week at the American Association for Thoracic Surgeons, some Chinese surgeons presented doing a lobectomy. Okay, now when you hear the pulmonary artery, that bleeds at 4 liters a minute. Okay, doing a lobectomy 1,000 miles away from them. Okay, and 50 miles away. So the patient it was being operated on, and they were using robotic surgery to do it. Now, the Da Vinci is remote surgery, in my opinion, too, because we sit at a console and we operate a patient that's 20 feet away. But the point is, this was 1,000 miles away, and I'm sure it's ideal, but it does show what's possible with the technology.
Well, I think
I think what it shows is latency is not an issue anymore. You could sit in like from New York to Paris and operate on somebody, and you can scale expertise that way. I mean, it's still not AI, it's still humans in control, and it's still a master-slave relationship. But you're right, a lot of those uh, IT limitations, like network bandwidth connectivity problems, are now not so much a problem as before.
Yeah. No, and I think for the non-surgeons in the audience, I mean, there are certain things like operating deep in the pelvis and prostate surgery and some of the gynae surgery are places that are technically very difficult to operate in, and therefore having robotic instruments and robotic hands to go down there has made us better surgeons and has, do better operations in those difficult areas. And I sort of see, autonomous surgery as being more possible for things we can't do, like intravascular surgery. Like, what if you had something that could go clear a blockage in a robot that would clear a blockage in your coronary artery or something like that? Those are the kinds of things where I think that as the technology gets more able to go places where we can't go as humans or can't see, that's probably where we'll have that kind of capability.
Oh, I completely agree. I think there's so much hype in automation, lots of hype, lots of money being thrown at physical AI and its promises. Some of them is well founded, some of them is not. And I think to your point, it's really important to identify the unmet need, the problems. Why do we need automation? Do you really need automation of every little things? Perhaps in some situation it is very important and needed, and I think that speaks to that.
We got a comment from AI on AI. Adina.
Shaf, hello. It's so good to see you. Hi, Amin. Hi, Barry.
Hey, Dina.
I'm post-op, so I'm sort of, but I wanted to come on camera. Don't worry, the bottom is pajamas, the top is nice. I just wanted to say, first and foremost, thank you to each and every one of you who is on here today. I came on camera, even though I don't feel well, to say thank you, not just for me, but for all patients. And Amin can attest to this. I really did not have any background whatsoever in AI, and to Shaf's clever nod, I now have a newsletter, AI, my initials, AI on AI, and Amin and I collaborate on things related to breast cancer. So just to say to all of you, like, you're so brilliant and so capable. So if I can find a way to contribute to the field, you definitely can. So please, please, please don't be intimidated, and love you all so much.
Thank you, Adina.
Thank you, Adina.
Caesar, you had another question, comment?
Yes, I'm sorry. I don't want to hijack your presentation, Doc. It's just that I'm really excited. This is the first time I've seen something useful. 2 questions. Would it be valuable if during the procedure, we kind of like take biomarkers, plasma samples and so forth to ingest it in the model and have like a more like biochemical and macroscopic integration of the the surgery or the procedure or the case?
You can do whatever you like with AI. I think that's one of the beauties of deep learning. You can put a mishmash of every type of different forms of data to make creation of multimodal algorithms. And you can do it now. Is it needed is another question. Like, will the biomarkers necessarily help predict a go or no-go zone? I would say unlikely, but it could be helpful. I think in the future we're going to see an integration of every type of data about the patient. Their video data, their radiological data, their biochemistry, their past, their chart, all that data integrate into personalized copilot to provide us with decision support, probably. But we're not really there yet, at least for the use cases that I do.
Well,
but Shaf will attest to.
Yeah.
Oh, sorry, go.
We have, what we've done in lungs, right? Like a lot of the
I was
data.
just gonna say that. I was just gonna give you a shout out.
No, but we literally have 300 or 400 parameters per hour coming off the lung. And there's biomarkers, there's physiology, there's imaging, there's flows, there's physical parameters, and they all put together. And so what Andrew did is he built that algorithm of insight to guide surgeons. Is this a good lung or not? Surgeons have never had that many parameters a minute in so many different dimensions. And now we know which biomarkers are predictive of a good lung, which pulmonary artery pressure, which vascular resistance, which gas, which compliance, which everything, which video, which x-ray. And now what we're finding is the surgeons that do a better job are the ones that can assimilate this data. So now we've put together all of the parameters together, just like you mentioned, Caesar, to say, okay, if you put all of this together, can you say this is a good lung or this is a bad lung? You know, and the other part to create confidence for the surgeon, which said this is a good lung. These are the top 5 parameters that the algorithm used to tell you it's a good lung, or this is a bad lung, don't transplant it. These are the top 5 parameters that characterize this as a bad lung or a dangerous lung. You know, and then the digital twin work that we published just a couple of days ago in Nature Biotech is exactly that. Can you predict where this lung's going to be 4 hours from now, so that you can actually modify it and improve it? So I think you do need to find your use case, and some of them are there. Some of them are still AI just looking for an application, you know, and we have to sort of figure out where to use it best.
But pay attention to the question that Shaf was answering. Is this a good lung? That's a very different question than where do I dissect? That's like very focused on purely on anatomy. But like the question of is it a good lung is such a big multifactorial thing where we're having all that analysis of all the biochemistry and all the data points and the ventilation parameters, and like that's all, like, I'm sure has a complex interplay to it, where AI can be extremely valuable. So as like you said, depends on the use case.
Awesome. Appreciate it. Thank you.
Any other questions? Comments?
I think you got everybody very excited. I mean, as usual.
Oh, thank you.
For being here. This is a great round, and we're over time. So thanks everybody for attending. It was great having your presence. Thank you.
Thanks for having me. Bye, everyone.